Hi everyone, welcome to Vijay Datta chemistry classes. This is Purnima ma'am. So today we are going to uh, discuss about the Dalton's law of partial pressures, right? So this is very important. What is this Dalton's law of partial pressure? And let us see some applications on Dalton's law of partial pressures also. So what is meant by partial pressure first of all? So Dalton's law, what is the Dalton? John Dalton in 1801 established the relation between the pressure of the mixture of gases and individual pressure of the constant gases. That is only we are studying as Dalton's law of partial pressures. So he brought the relation between the individual gases and pressure of the individual gases and pressure on the mixture of the gases. Okay, that is only partial pressure, that is only law of partial pressures here. When see, if you are taking the different types of the gases in the different containers, suppose if you are taking N2 and plus H2 in one container, they both will react and they'll form NH3. If you are giving in some special conditions, if you are maintaining temperature and pressure, that will be the Haber's process, like, right? So when different gases, they'll not react chemically. Means I will take here helium and oxygen. Helium is chemically inert, it will not react with any other gases. So when different gases that do not react chemically with each other, they kept in the same container, they intermix rapidly. What happens actually, they'll intermix rapidly and exert some definite pressure. They have to they'll not react chemically, but they'll intermix to each other physically. Just they intermix and they exert some pressure, and each of the gas in the mixture exerts its own individual pressure. We are not talking about the gases which are chemically reacting, we are talking the gases about which are not reacting chemically. Those gases, when they are mixing, helium and oxygen both are mixing, they exert some pressure. At the same time, itself helium exerts some pressure and itself oxygen exerts some pressure. That pressure is the pressure of the individual gases, pressure of oxygen, pressure of helium. Like that only, pressure exerted by the mixture of the gases, helium and oxygen both will exert some of the gases. So he wants to bring the relation between these gases, individual gases pressure and a mixture of the gases pressure. He has done some experiments in the 1801. John Dalton, he brought the relation between the sum of pressure of the mixture of the gases and individual pressures of the constant gases. This relationship only we are going to study as the Dalton's law of partial pressures. Okay, this is called Dalton's law of partial pressure. See here, at a given temperature, it is the temperature constant, means conditions same. At a given temperature, total pressure, total pressure exerted, total pressure exerted by two or more gases, two or more non-reacting, means they are not reacting chemically, non-reacting gases occupying a definite volume, occupying a definite volume is equal to sum of its partial pressures, sum of its partial pressures. What is meant by partial pressure? Partial pressure is nothing but the pressure exerted by the individual gas. That is called partial pressure. Okay, total pressure is nothing but the mixture of the pressure. Suppose in this container I am taking A, B, C, three types of the gases which are non-reacting chemically. They are not reacting, so the total pressure exerted by this container is, I am considering as the TP, means total pressure is equals to sum of its partial pressures means individually A exerts some pressure, individually B exerts some pressure, individually C exerts some pressure. That is what I am taking as PA plus PB plus PC and so on. Not only three, you can take different types of gases also. Suppose the total pressure you can write as PT also. Total pressure equal to sum of its partial pressures. The definition for partial pressure is nothing but the gas exerted by the the pressure exerted by the gas individually is called the partial pressure. This is the Dalton's law of partial pressures. This is the statement. Here P is T is the total pressure and PA, PB, PC are the partial pressures of the A, B and C respectively. Right? So the pressure that a component of the gaseous mixture would exert if it were only in the volume under consideration at a given temperature. That is what very important. When this law is applicable at a given temperature, if you are keep on changing the temperature, then we cannot consider this statement. This statement is applicable when we are taking at constant temperature and we are maintaining certain volume, because while temperature is increasing, volume also either increases or decreases. That is what, right? So PV equal to nRT according to that, according to the Charles law, right? V proportional to T. If temperature is increasing or temperature is decreasing, when temperature is increasing, then obviously see here volume V proportional to 1 by V based on those relations. V proportional to T based on these relations, V1 by T1 equal to V2 by T2. V volume is directly proportional to its temperature. Okay, so based on these conditions we can consider the partial pressures. Got it? So volume also we have to maintain the constant temperature to calculate this partial pressure. And see here we have a derivation for the Dalton's law of partial pressures. What is the derivation? Here let N1 and N2 be the number of moles of two non-reacting gases A and B. Number of moles of A, 1 and 2. Okay, you can take Na and Nb also. Number of moles, right? Volume, no, we are taking a filled with certain volume and we are maintaining a constant temperature, right? So we have to calculate the total pressure exerted by the container. We have to calculate. Then obviously ideal gas equation PV equal to nRT, but N is nothing but Na plus Nb, because here we have taken the two gases. We are maintaining the pressure, we have to calculate volume and temperature are same. Then R is the universal gas constant and temperature. PV equal to nRT. Actually, this is the relation, right? Because pressure is vary, but volume and temperature we have taken fixed, and Na and Nb are the two different number of moles for A and B. We have to calculate the individual partial pressures, isn't it? Individual partial pressures. Individual partial pressure of A is the partial pressure of A into V equal to Na into R into T. This is for the par A case. If you are taking the partial pressure for B, PB equal to NB into RT. This is the partial pressure of A and this is the partial pressure of B. This is the total pressure exerted. This is the total pressure. 2 and 3 are the partial pressures of the gases what are given. So if you add 2 and 3, then PA into V equal to Na into R into T, then PB into V equal to Na into R into T. So if you are adding is nothing but volume is the same here, then I am taking PA plus PB, which is equal to RT are same, then I can take Na plus Nb, right? This is only no, if you are adding the equations we are getting the final relation is this only, no, that is partial pressure of A plus partial pressure of B into V equal to number of moles of A plus number of moles of B into R into T. This one I'll consider as the fourth equation. Now, if you compare 1 and 2, what is the first? If you compare 1 and 2, what is the 1? PV equal to Na plus Nb into RT. So, according to this is the first equation. According to the first and second, according to the first and fourth equations, V is V, Na plus Nb, remaining all are same. Then the P equal to Pa plus Pb. This is Dalton's expression, ma. This is Dalton's expression. See here, dividing equation 2 by 1. See, 1 and 2. This is called partial pressure. Total pressure is equal to sum of its partial pressures. This is only Dalton's expression. Here, you want to calculate formula for partial pressure. Then case 1. Partial pressure of A you want to calculate. Then you can go, you're dividing equation 2 by 1. 2, so what is the second equation? 2 by 1 I am doing. What is the second equation here? 2 is the PAV by NART, right? So PA into V equal to Na into R into T by, what is the first equation? We know that is the first equation is P into V by Na plus Nb into RT. Then see R R T T, volume, all are getting cancelled. Then what is left? Pa by P equal to Na by Na plus Nb. What is this Na by Na plus Nb? This is only the mole fraction, number of moles of A by number of moles of the solution, right? So this one we can write as XA. So P A, partial pressure of A by total pressure P equal to XA. Then I want partial pressure of A, formula is XA into P. Similarly, you can calculate for PB equal to mole fraction of B into total pressure. So individually you can calculate the partial pressures like this also. Mole fraction into total pressure, mole fraction into total pressure of the respective gases. Okay. This is the partial pressure formula is mole fraction into total pressure. Okay guys. So and this is about the Dalton's law of partial pressures statement and its derivation, how we have written and how to calculate the total pressure and how to calculate the partial pressures also we have been given here, right? Okay, guys. Thank you. These exemplar problems and the diffusion and effusion we'll see in the next class. Okay, guys. Thank you. Thank you so much.